How's everybody's weekend? Who had the best weekend? Nobody? Are there midterms coming up for people yet, or not yet? Okay, there's a note packet. Again, it's printed out on the table thingish over there. It's also under the topic 3 Q folder if you want an electronic copy, the quiz practice.pdf file here. And we'll be spending most of our time today going over that note packet. If you recall, last time we were working on this counting quiz note packet that's different than what we're going to go over today. The counting is what you will have a quiz on next class period on Wednesday. And then the material that we're going to go over today is looks like this, the memory management. And we'll have a quiz on this, not this week, but the following week. So like 10 days from now. Both of these two topics are, I think, the most important foundational topics for the course. So if there's like 1 week that you focus on this course and make sure you don't fall behind, it's this week. Whatever material you don't understand this week, you will have to understand it at some point in the future, or you will just be getting zeros on all the subsequent assignments. So if it takes, like, I don't know, buckle down and spend 30 hours this week to make sure you fully understand these two notes packets, then it'll be worth it. Hopefully it won't take that long though. The counting stuff, we're probably not today going to get into more advanced version of the counting, but definitely this week we will. We'll need it for the lab and the homework this week, but it won't be on the quiz. The quiz stuff is just what's here printed in the counting notes. And any questions about anything administrative? Other quick announcements. So I was really very pleased during the lab sessions about how well people were collaborating and working together with each other. It's oftentimes a struggle from my perspective in CS classes to get students working together. My other class they don't like working together. But you all did really well, so I was very happy with that. So good job on that. Again, the collaboration policy of having to work together in these designated spaces like the lab session time or at the QCL. Really, one of my goals for that is that I think it's actually going to encourage more collaboration between you all. That if you know that like there's going to be people at the QCL who you can work with, then even if you feel like maybe you don't know people in the class as well, I hope is that you would still go to the QCL and seek out those other people to work with them. That's just, there'll always be people there to work with. So we still have the homework assignment that's due tomorrow from last week. And if you haven't finished that, that's totally okay. But you'll have lots of opportunities at the QCL to work with people on it. Grades should be totally up to date in Sakai. I'll try to keep them up to date every week, just entering stuff as we go, but they are totally up to date. Lots of students, for whatever reason, doesn't matter, but still haven't submitted the first assignment on Sakai. If that's the case for you, then I've just entered in zeros in that assignment, but you can still submit it. The policy was there's no late penalty for that first assignment, so you can still submit it to me. If Sakai doesn't allow you to do it on Sakai, just send me an email. And no late penalty will be applied, but you should just know that you are officially behind at this point if you were struggling with that and haven't finished it yet. Any questions about anything? Okay. So we're gonna come over to this note packet. And I'm going to be doing everything inside of Python Tutor today to explain what's going on in this note packet. I also have a bunch of little notes already written here inside of this note packet that I think fully or try to describe the behavior that we're going to be seeing and the things to be looking out for in these problems down here. Definitely you should make, there are a lot of problems on these note packets. If you, for whatever reason, can't feel like or can't get through actually working through all of them, that's okay. You're not required to work through all of these problems. But the notes up here, you should 100% understand like every word, why I included that word in these notes. Because if you don't, then there will be things on the quizzes that you'll miss, both in this first quiz on memory management and all the subsequent quizzes and problems that include this concept inside of it. So I'm going to switch over to Python Tutor, and that's where we'll be working today. Again, I recommend for the purpose of taking notes today, do the notes on your packets so that you'll have access to this when you are working through the quiz. I'm going to try to, at least at the beginning, follow the pattern of what's printed here in the problems in the Python section. Again, between the EOF and EOF, this is the Python code that we're going to be running. But as we go on, I'm going to stop following the notes here exactly and just illustrate the concept directly in Python Tutor. So what I have pulled up in Python Tutor over here, let's make it a little bit bigger, I believe is just exactly what the first Python problem is. Oops. Slightly different. ys.append. We'll do it that way. ys.append of a like this, and we'll visualize this and talk about what's going on. So this copy library is something that's built into Python. You'll never have to install this, no matter where you're working on the Lambda server or any machines in the future. It's just built into Python, and because it does it's very important. You can't implement most algorithms without this library. And then over here, again, in this global frame section, every time a variable is defined, the variable comes down here. So copy, anytime you import something, it turns out this is just a variable in Python. And so we have a copy down here. And then this arrow to this thing called a module instance, which we don't really care about exactly what that means. The important thing is going to be this XS variable right here, and it has this arrow over to this list over here. Again, anytime I'm creating, when I'm coding or on these quizzes, when I'm creating these sort of containerish objects, things that contain multiple things inside of them, I always add an S to the end of the variable name just to let myself know that it's a plural thing. And so it's a container. So this XS is something that contains lots of X's, and in this case, it contains 3 of them, 1, 2, and 3. And the first tricky-ish thing here is going to happen on line 3. And again, in Python Tutor, when we have the red and the green arrows over here, the green arrow is the last line that was previously executed, and the red arrow is the line that we're going to execute next. So we're going to do this ys equals xs. So I press next. And when I do that, what you can see is this arrow was created right here. Both of these two arrows, both of these two variables pointing to the same list object over here on the right-hand side. So these are just 2 different names for the same exact thing. And so if I modify one of these variables, whether it be xs or ys, then the change will happen in both of these variables because they're both pointing to the same object over here. And we'll see that on line 4 over here when I do this ys.append of a. This is going to come over here, ys, follow this arrow over here to this object, and do the append operation, putting a at the end, like that. So 1, 2, 3, and then a. And then I'm not going to actually inspect ys in order to see what the change was. I'm instead going to inspect the xs variable down here. And when I do that, we get the 1, 2, 3, a up at the top. And so this would be what I would expect for your answer on the quiz to get full credits. The key thing here is that this is an assignment operation. So we're saying that ys equals xs. And what that does is we don't make a copy of the object over here. Whatever's on the right-hand side over here, whatever the actual data is, we don't make a copy of that actual data. Instead, we just have this little pointer thing or this reference reference the same object over here. I'm going to change this code. Yes, Henry. Yeah, at this point, we haven't used this import copy command. I'm going to edit this code next, and we'll see what some of the alternatives are to this assignment operator right here. And one of them that uses this import copy is copy.copy. Anytime we have a module, these things up here that we import in Python, we call them modules. Some people, a little bit informally, will call them libraries. In Python, a library technically refers to something a little bit differently. So the proper Python terminology for this is a module. And then in order to access the functions inside of this module or any of the contents of this module, we do the module and then a dot and then the function that we want to use. So this is going to access the copy function inside of the copy module. Very confusing that it's all named that way, but that's what's going on. And so all I've done, the only difference between this and the previous example is instead of doing assignment, I've used this copy.copy function right here. And let's walk through what's going to happen. Next, next. So everything's the same so far up to line 2. I'm about to execute line 3. I press next. And now you can see that there's 2 different objects over here, 2 different list objects, because we made a copy of the original list. And so when I do this ys.append of x right here, append, we only put the a value over here inside the ys list because we're just following that arrow over here to this list object over here and add the a to the end over here. There is no way in Python to like once you've made this copy, it's 100% totally separate things. There's no way to ever go back to this list without using a variable that references it. You can't in any way from ys figure out what was the original source, the original thing that was copied. And now when I execute line 5 right here, line 5 printing XS right here, going up to this list, again, not modified by the append because the arrow over here not pointing to this list, but to this list down here. Key difference again, copy.copy adds a separate list down here. And so all the operations on ys will only affect this separate list down here. The equal sign never makes a copy of things. Instead, it just gives you a different name that you can reference the same object over here. Any questions? Okay. Most students at this point, I think, usually find that this sort of makes sense. Maybe not 100% clear why things are the way this are, but if you just have code that looks like this, can reason through things. There's also, for most students, going to be a point in this note packets where suddenly things go from making like 90% sense to like 0% sense. And there's no like nothing in between, that it'll just suddenly like, I have no idea what's going on. So the important thing in today's lecture is to try to find, like, be paying attention so you can identify what is that cliff for you, so that you know when you're studying to go back to that spot and try to fix the understanding there. Yeah, pretty much impossible to like halfway understand these things. It's either going to be I know what's going on or I am totally lost. So the first confusing thing I think that we'll see is what happens when we do a list slice. So if you recall, in Python, we can do if we just have the square brackets like this with a number inside of it, this is called an index or a subscript operation. And this gives me back whatever the position at, or whatever the value is at this position. So XS at 0 would be 1, and so that would store 1 over here. If I want to actually get back not a value, but a list, then I can put a colon inside of here. And this will give me everything starting at here going to the end. So 0 to 1. We'll start with that. Visualize this execution. Next, next. And when I do this slice operation right here, this is the key thing that's very easy to forget, is that slice operations always implicitly make a copy of a list. So here, when I go from 0 to 1, this is saying take the first or the 0 position, go up to position 1, but not including position 1, and make that be our final list. So 0:1 down here, we get index 0 right here, go up to not including index 1, so it only contains this value right here. And this value is 100% distinct from this value over here. This list 100% distinct from this list up here. So press next again, add the A to this list, does not add it to this list up here. Next, still printing out 1, 2, 3 up at the top. Let's edit this code one more time. And here, instead of saying ys.append, if we say ys at position 0 equals A, then run this again. Here we go. We've created an entire new list again with this slice, lines 1 through 3, the same in this version of the code as the previous version of the code. And now what's confusing right here is that this ys of 0 is currently equal to 1, but this 1 is different than this 1 up here. So when I press next, we changed the 1 down here inside of ys. I'll go back, press next again. You can see that the 1 over here is changing inside of ys, not changing up here. So it's totally distinct list objects. Changes to 1, no matter what the change is, will not affect the other list object in any way. I'm going to edit this code one more time. Let's take away the slice for a second and just run it like this. So now we're not doing a copy anymore. We just have this assignment operator like this. So now the ys and the xs both pointing to the same things over here. Now when I do this index operation to set the A, we change the actual A value right here on both lists, and we get the A23 is what will be printed by the print xs up here, A23. Any questions so far? Yes. If you were to ys and do slice, say like 0 through 2, would that create a list? Yeah, so there's a great question. The question is, what if so in the slices that we've seen so far, it's only doing a sub list, a small portion of the list, but what if I wanted to take the entire list? And a common idiom in Python for taking the entire list in a slice looks like this. This is the part that gets confusing, that like, it's very easy to see something like this and not recognize that this is a list slice going on right here. But anytime you have square brackets with a colon in the middle, this is going to be a slice operation. And so this is going to take the entirety of the list and make a copy of the entirety of the list. Visualize that, walk through. So this is the key line right here, line 3. And we run that, and you see it makes a copy of a list down here. For some reason, in the Python world, or there's this mantra in the Python world that explicit is better than implicit. Edit this. So the mantra is explicit is better than implicit. And this is what we call an implicit copy, because we're not actually like explicitly telling people that a copy is going on. So ys equals copy.copy xs. This would be an explicit copy. This would be an implicit copy. And this is a model that people talk about all the time in Python. So this is better Python style down here. And in 90% of situations, most Python programmers do obey this. Explicit is better than implicit and will prefer the explicit operation. But for some reason, with copying, this is extremely common. And in the real world, you'll see this much, much more often than you'll see this. I think another thing is just programmers are lazy, and having to add this extra import at the top is too much for people. And so they'll just do this, and it's expected that everybody knows that when you see something like this, a copy of the list is being made. Good question. Any other questions so far? Okay. At this point, too, a lot of, I mean, there's some things to remember and memorize at this point. But I don't want to say it's easy at this point, but we're about to get into this part where it turns like really, really weird. And that's what happens when we have lists of lists. So I'm going to change us back to the implicit copy just for us to get more practice with the implicit copy right here, what's going on in an implicit copy. And so 4, 5, 6, and we'll change this back to doing the append, ys.append a, like this. And we'll visualize this execution over here. And the first thing we're going to see is exactly what does a list of lists looks like in this Python tutor over here in this object section. And so we have an arrow from XS over to this list over here. But in this list down here, we don't actually have values inside of this list. The XS list does not contain any values because it contains references to these other lists. So this first one right here is a reference to this top list, 1, 2, 3, and the second one down here is a reference to this bottom list. Now, when I make this copy right here, ys equals xs implicit copy, list slice right here, implicit copy, I press next. What we're going to see is that we did in fact make a copy of this list right here, but we did not make a copy of any of these sort of they're not sublists because they're not actually contained inside this list, but sometimes we call them children lists because this is like a parent that's pointing to its child up here. So both of these two lists up here, we would call them children of this list down here. And there is no actual name directly for these lists. Objects that exist in memory don't have to have a name of a variable anywhere in Python. We can reference these objects by doing the subscripting of this list down here. These lists are just, but they don't have their own actual name. And so down here, we've made a copy of these two lists. And on line 4, we're going to append the letter A to this copy down here. Let's pay attention to what's going to happen. I'll press next right here. We've just executed line 4 right here, appending the A. And notice that we add this A down here. The A is just a value. It's not a container in any way. So there's no arrows pointing anywhere else. We just add this A. Does not affect the XS list right here, does not affect this list at all. And so when I press next, we still print out just 1, 2, 3, 4, 5, 6. This is, I don't know, what you might expect the copy would do. It's how the copy's been behaving before, that when we've been operating on the YS list, which is a copy of XS, modifying YS does not modify XS. Now we're going to get to the weird part. What if I do the ys? So ys at position 0 will give me this list right here. And then I'm going to do an append to that. Append A like that. Visualize this execution. Walk through again to these first 3 lines, all the same. So this is our same setup over here with these objects. We have these children lists, 2 children lists. They were not, no copies were made of these children lists. Only copies were made of these parent lists down here. When we did line 3 right here, I'll press previous, go back to line 3. There is no YS line running. Line 3 makes a copy of YS down here, does not make a copy of these lists up here. YS and XS are 2 different lists, but they point to the same lists as their elements. So here, when I do YS at position 0, follow YS, go to position 0 right here, follow this arrow up here. That's going to give me this list up here. And when I append A, press next, I append A, we added A to this list up here. Well, this list up here is also inside of XS. XS down here, arrow right here to this spot right here. And now this arrow on XS points to this list up here, which contains the A inside of it. So when I press next right here, even though I made a copy of the YS list right here, even though I made a copy, we were still able to modify the contents of the XS list in this way. So this A value up here still got added to the XS list, even though I made a copy right here. I'm going to edit this code one more time. We'll see a different version of this. Now I'm not making a copy. I'm just doing an assignment operation right here. Visualize this execution. Walk through, walk through. So now there's no copy down here. YS, XS pointing to the same list down here. And so now it makes sense when I modify the this list by adding an A over here. It's modifying the same list because we're using the assignment and not the copy. But when you have lists inside of a list, it doesn't matter whether you use assignment or copy, you're still going to be modifying the this internal object over here. And this object is the same object that both of these two lists are being referenced. The only thing that the copy is making a copy of, it's just making a copy of this arrow. So it's a different arrow, but the arrow points to the same exact thing. Very easy to be confused about this, and very easy going forward to think that you're understanding what's going on at this point, and then suddenly realize when we see more examples that the examples aren't behaving how you think they should, because you missed a subtle point about things. But the key thing here, again, is that copies, a copy only copies the actual object and not any of the things that the object might point to. Are there any questions at this point? Okay. So what if we want to actually copy everything and not just the object itself? That's where this copy.deepCopy function comes in. Deep copy says don't just copy the actual list, but also copy everything that the list might happen to point to. So the first two lines here are the same. The excess variable created like this. And now on line 3, I press next, scroll down over here, and you can see that the ys variable has a totally separate set of lists that it's pointing to. Not only the parent list down here was copied, but also all of the children lists over here also copied. And so on line 4 right here, when I do this append A to the child list of ys at position 0, that's only going to affect this list right here. That's only affecting ys at position 0 list and not affecting the list at XS at position 0. This list up here does not change because the deep copy made copies not only of the parent, but also of the children. And so when I print out the XS down here running the very last line, then we'll get a result as if the list was not modified at all, because it wasn't. Again, summary, deep copy copies not just the parents, but also the children. Copy copies only the parents. Assignment copies nothing. We saw that there's an implicit way to do, this is the implicit copy, and there is no implicit deep copy. If you want a deep copy, you have to actually use that copy.deepCopy function. On your homework assignments for this week, you're going to have to be making copies of things, and it will be tempting to use the deep copy function because the deep copy function seems easier to think about and easier to reason about. But it is almost always a mistake, to use the deep copy. 99% of the times when you want to copy something, you want to use the shallow copy, we call it. So copy.copy is a shallow copy because it's not deep, so it must be shallow. And this is the thing that you want to do 99% of the time. I was trying to think this morning of if there's ever been an example in my life, I've been programming over 20 years, if I've ever wanted to do a deep copy. And I'm sure it must have come up at some point, but I can't think of any time in my life when I've wanted to do a deep copy. But these shallow copies are things that I do on a daily basis. So yeah, deep copy seems simpler, seems easier to reason about because it actually makes copies of everything, but almost certainly not what you want to do in practice in the real world. Yes, Henry, sorry. Question is, what if you have more than just 2 lists like this nested? Deep copy doesn't matter how deep it is, it'll go forever. The shallow copy only ever does the parent, no matter how many there are. And there's no way to do something in between. Yeah. Yeah, good question. So let's modify this problem a little bit. And I think this is what you were asking here, is that here we're doing a shallow copy of the XS list up here. So we're only copying the parent, not copying the children. The parent got copied. It is referencing or pointing to the same children objects over here. And then we do the ys.append a over here. This affects only this parent over here. And then the question is, what's going to happen when I actually print the ys or do something with it? And the answer is that, yeah, so here's the xs again, no changes. But if we come down here to the ys, we will see the change down here. That we have this a variable that got added to the list right here. Did that answer the question? Great questions. Any other? Yes, Miles. Sorry, I couldn't follow that. So in this case, the change that we made right here, line 7, used to not have this subscript operation right here, just appending a directly to the list here. And so when we were appending a to ys itself, ys is the thing that we made a copy of. But now when we have ys at position 0, this is a thing that was not made a copy of. And so when we append to a, it's going to affect the thing that was not copied, affect this list up here. And so both of these two lists, both XS and YS, both of these two lists point to this same child over here as their 0 position. And so both print out the same contents over here. So this shallow versus deep copy has different names in different programming languages, but this is a concept that exists in every programming language. And no matter what language you're using, somehow you have to, at some point, deal with this. What we're going to talk about next, though, is something that is very Python specific and something that only exists in Python and is a major source of bugs that people encounter both in this class and the real world. So actually, yeah, so assignment versus copy versus deep copy. This is also a pretty major source of bugs. This is the sort of thing that an experienced developer in any language they're going to have in the back of their mind, though, about like looking for these problems. What we're talking about next is even experienced Python developers often don't know the details that go on here. And so they can spend a lot of time fighting with bugs and not understanding exactly what's going on. This is very common, especially for people who learned different programming language as their first language, like C++ or Java, and then switch over to Python later because they miss some of these Python specific things. And this is what happens with what we call default arguments. A default argument in Python is anytime we have a function, and so here, like def foo x equals 4 right here, this 4 is the default value for x. I'm going to switch over to Python Tutor again, and we'll just totally erase this. And def foo x equals 4, x plus equals 1, return x, and just copying over basically what's in that quiz problem right now. Numbers are probably a little bit different, but that'll be okay. And we'll visualize the execution right here. Again, when we define a variable, when we define a function, we don't actually execute this function. So the red line here, the line that we're going to execute next, will not go inside this code block, but it will jump over this code block and down to line 4 right there. Press next, jump over down here to line 4. And so you can see there's this function foo over here, and then there's this weird like default arguments thing that was created down here. And the behavior of this default arguments is what's going to be weird. Let's press next again. And so we're on line 4. I used to be on line 4. We're executing line 4 right here. When we execute this line, it means we're going inside this function, actually running this function, evaluating that function. We'll go inside of it right here. And when we go inside, you can see this new box down here was created. This box in Python terminology is, again, technically called a frame. And this is the foo frame because we're inside the foo function. And the frame is what stores all of the local variables that we have access to when we're inside the function. These default parameters or function parameters in general are always going to be local variables for that particular function frame. And I'll press next again, and here we have x plus equals 1. Press next, and you can see that this modifies the x value in the foo frame, modifies the x value in the foo frame, but does not modify this default arguments over here. And so the first principle over here is that when we have what's called a primitive object in Python, that is an object, there are 4 types of primitive objects in Python. I'll write this out. 4 primitive objects: integers, floats, strings, and booleans. These are called primitive objects because they can't be modified directly. Instead, like anytime you have an integer and you add a number to it, it just literally creates an entirely new integer. It doesn't modify the existing integer. Primitive objects and non-primitive objects behave in Python differently in certain edge case situations like these default parameters. And so if you just memorize that these are the 4 primitive objects, that's just all there is in Python, and there will never be more primitive objects. And everything that is not one of these 4 things is a non-primitive object. These 4 things, primitive objects in Python, when you modify them inside the function, it does not modify the default value up here. It does what you expect. So let's run through this again. Here we're modifying the x down here, modifying the local variable on line 3, saying x plus equals 1. X plus equals 1 modifies this x down here. Press next, changes that 5, return 5, return 5. Up here in the global frame, we now have y is equal to 5. And come back in here, x plus equals 1. This x is now reset to the value 4 because the default argument over here is 4. So when you have a primitive object that is your default value, you can basically ignore, for the purpose of the quiz, ignore all the stuff that happened up here because it doesn't matter. It's not going to affect things. The only thing that's going to matter is the very last function call, whatever we use as the parameter down here in the last function call. Here we're not passing something in, so it's using the default value of 4. And let's see. Here we go. So we're on line 8 right now, about to execute this last run into the function. Go into the function, x will be equal to 4. Set it up to 5, return x, return value 5 right here. And then the y will take the 5 value and we'll finally print out 5. So the default arguments work like you would probably expect them to do whenever you have a primitive object in here. And that means that changing the value itself down here is not going to change the argument up here, not going to change this up here in any way. This is not going to be true, though, when our default parameters are non-primitive objects, or when they're containers. When we have something like a list, like xs equals 1, 2, 3, like this, and here when I say x dot append a, and let's return length of xs like that. Let's make that an actual list. I don't think there'll be any Python errors here. When I do this, now on line 2, when I define this function, it's not only just defining this function, it's also going to create this object for us over here. So I'll press next, and you can see that over here, it defined this foo function, and then in this default arguments, this xs is this pointer out to this list object over here. And every time I go into this foo function, so I just ran line 5 right here, we're going inside the foo function right now on line 5. We did not pass a variable, so the xs over here, its default value is going to be whatever this xs points to over here. this XS is pointing to this object over here. So this 1, 2, 3. And when I do this XS.append A right here, it's actually modifying this object out here. It's actually modifying this object that this default argument right here, this XS points to. XS right here points to this thing over here, 1, 2, 3, then the letter A. So when I run through this program again, like right here, on the second time I use this with this foo function, even though I have a default argument up here specified of 1, 2, 3, it looks like this this foo function right here, just looking at this code, is going to have 1, 2, 3 inside of its XS variable. But when I press next, come up here, you can see that this XS is still pointing to this thing up here. And so it's actually got an A inside of it now. And now it'll have 2 A's. And then here, when we do this foo with the list 2 right here, we're not using the default argument. So this XS will be pointing to this 2 over here. We'll append this A to this 2 list right here, because this list was not the default list, but a different one that we specified. Add the A down here, not add the A up here, because this XS does not reference this. It referenced this as this thing down here. Press next, return the length. And then the very last time through the foo function right here, once again, we are using the default parameter. So I'll press next, come up here. This default parameter, this arrow gets copied over here, points up to here, and 1, 2, 3, AA, append this last A right here. And now when we return the length of XS, the return value is 6, because there are 3 A's that got appended. The 3 A's that got appended again correspond to these 3 function calls that do not have a value passed in for the XS and that are using the default argument, which is this one up here. So I press next again, and Y is going to have a value of 6 down here. Very confusing that it looks like this XS should be reset to 1, 2, 3 each time, and we'll always start off at 1, 2, 3, but that is not the behavior. That anytime you have this default parameter like this, this object, this list over here, is going to be the same object for every time we pass it in. And so any modifications that you make to it inside of a function, those modifications will propagate, and very easy to have bugs that way. Very strongly encouraged practice when you're programming in Python is therefore when you have a default argument, never modify it. And if for some reason you must be modifying the object in the function, then never provide a default value. This is I don't know, a simple to state rule, but it's easy to forget about when you're programming. That often it'll be tempting to provide default values up here. A lot of libraries actually provide default values up here, and have this very unexpected behavior because they modify that default value, and so it can lead to these unintuitive consequences. One of the things that, and I've said this before, but one of the things that ends up separating successful programmers from the unsuccessful programmers, the things that the programmers who make millions of dollars at Google versus the ones who don't, is, well, first of all, something that does not separate them is raw intelligence. That's one of the things that people often think about with programmers, is that like the more raw intelligence you have, the more that you can understand these weird edge cases that are going on. And so you can write more complicated code because you understand more of what's going on. And no matter, like, I don't know, Even if you have an IQ of 300, the computer understands a lot more than you do about what's going on inside of the computer. And it is impossible for any human to follow along what's going on inside the computer. So really what separates the most successful programmers from the not as much successful programmers is the ability to like just understand why we have certain rules of thumb like this and follow those rules of thumb, follow these best practices. Because if you follow this best practice, then you will avoid having to waste lots and lots of time debugging your code based on issues like this. Question? So yes, there's a great question. So in this, I think there are some quiz problems that do this. The question is, what if we were doing something like import copy right here? And then down here, we did something like xs equals xs or equals copy dot copy of xs like that. Visualize that execution. And now in this case, when we step through it, the line 4 right here ensures that we make a copy of this object as soon as we get inside of the function. And so the append that we do on line 10 right here will affect the copy, but not the original. And so no matter how many times we run this function now, the function will always give the same results with the same default parameter. Is that a good thing to do or not a good thing to do? Depends on the exact circumstances of your problem. We're going to be talking here very shortly about runtimes of algorithms, and we'll see that this copy command can really slow down your program. So it's ideal to avoid doing the copies whenever you can, and better to just, if you have a default value like this, not modify it in any way. It's a great point. Any other questions so far? Yes.
Can you just say that this is something, but is there some kind of runtime?
Yeah, the question is, why do we have this fundamental difference in behavior between these primitive objects and these non-primitive objects? The answer has to do with performance, that having these arrows, having these redirections, having these references or pointers to other objects turns out to, it causes a lot of overhead that the computer has to deal with. And these objects are so often used and so fundamental that Guido van Rossum, our benevolent dictator for life in Python, decided that for performance reasons, it's ugly that these 4 things are going to behave differently, but we don't want to have that redirection that slows things down. And so these don't redirect. Yeah, the well-written Python compared to well-written, say, C code typically is about between 100 to 1,000 times slower. Python code is 100 to 1,000 times slower. And one of the main sources of that slowdown is that Python is creating all of these redirections and things for you under the hood. Other languages force you to manage these redirections more explicitly. And when you manage them more explicitly, you can get your code to be faster. But usually we don't care about like whether something runs in 1 millisecond or 10 milliseconds. And so for our purposes, Python is fast enough. We just have to understand these weird edge cases. And but other programmers in other languages have to go into even more details. The fact that these default parameters also have this weird behavior of modifying each time is also a performance optimization. And pretty much every time in this class, when we get to like a weird thing, that why is it weird, it'll be somehow for making Python code a little bit faster. Good question. Let's come back over to, here we go. So we've talked about all the default argument stuff now, and let's scroll down a little bit more. The last section on this notes is about reversing a list. And there's no new programming concepts throughout most of this. Instead, what this is really emphasizing is a practical application of all of the memory management issues that have been addressed in the previous portions of this notes. Reversing a list is something that is a very common interview question, especially for students who are just coming out of a data structures class looking for an internship somewhere at, say, Google or Facebook or Microsoft or these sorts of companies. If you're applying for an actual job, then usually the interview questions will be more advanced than this. But for like an interview for somebody who's just had data structures, this is one of the go-to questions that people will ask. And the reason it's one of those go-to questions is because it really, really tests your understanding of memory management. And when you're working at a company like Facebook, hundreds of millions of lines of code in Facebook.com, you really have to have this grasp of memory management for your code to work well and not have bugs that's going to bring down Facebook. So we're not going to talk about the details. I'm not going to go through any examples here, but on your quiz, very likely that there will be 1 or 2 or possibly up to 3 problems just from this section, because this section is very much incorporates all the previous material and has good applications. So focus on looking at that. I do want to just take a look at one note about this in Python. And so if we have xs equals 1, 2, 3, and just set up our basic problem like we had at the very beginning, print ys equals ys. And what we're going to take a look at is that Python has some built-in operations for reversing a list because it's just a super common thing to want to do. And there's 2 of those built-in operations that behave differently. And so we'll take a look at exactly what those built-in operations do. The first of those operations is dot reverse, like this. If we have a list up here, so this first line, line 1, saying xs equals 1, 2, 3, and then ys equals xs dot reverse, and then we'll print out both of those values and see what happens. Anytime in Python where you have a function like this that sits to the right of a dot of a container, xs dot reverse, like this, you should think of this function as it's probably going to modify this container somehow. And so if I press next right here and then press next one more time, you'll see that this ys variable, ys is actually none. The return value of xs.reverse right here is none. So that's the first thing to observe. The return value of xs.reverse is none. If I press previous, and we'll redo this line here. So we're on line 2 right now. Now notice this object over here, 1, 2, 3. If I press next, goes to 3, 2, 1, actually modifies the list to put it in reverse order. So if we print out both of those things, the XS list will be reverse order. The YS list will have none as the contents. This is the first way of reversing a list in Python, is by adding this dot reverse at the end of a list. Actually, in general, this is not a not the one that you probably want to use, though. Instead, what you probably want to use looks something like ys equals reversed of xs. Here, so first notice that up here, this is not a, or this function up here contains a dot. And so the functions that are the object dot reverse or object dot something, in general will modify the object. This one down here is not xs dot. Instead, the xs is like a parameter to the function. And these functions tend to not modify the xs, tend to not modify their containers. There's nothing in Python that stops this function. Like you could create your own version of this function like this that does modify it. It's just in general, it's not Pythonic for these functions to modify it. So this is not going to modify this at all. Another Pythonic thing is that functions that don't modify things are usually past tense, so reversed. That this is going to return a list that has been reversed. Whereas the things that are going to modify the list, this is in the imperative tense. It's a command. We're saying reverse XS, change yourself. But this one is past tense, like give me something that was reversed. And so I run that. And if we come down here, run that, you'll see that we get this weird list reversed iterator instance. Again, well, I'll just go ahead and print it out, see we get this this angle bracket thing up here with this weird random looking number up here. We're going to be talking about in a couple of weeks exactly why it does this and what the meaning of this is. But anytime on like a quiz, if I'm using one of these functions that makes that ends in a D like this, I'll be passing it to the list function like that, so that it actually converts that thing into a list. And here you can see that it's actually making a copy of the list down here that has been reversed. So the past tense gives you a copy of things where that verb has been applied. The present tense, imperative tense, does not give you a copy. It actually modifies the container in place. This one is a little bit more, a little bit faster than this one down here. But again, if we're using Python, we're not using Python because we want things to be fast. We're using Python because we want things to be easy. And this thing down here is a lot easier for us to reason about and work with, because anytime we're modifying one of our containers, that's just something that could possibly go wrong about we thought it was one way when it's actually been modified to be something else. So it's usually better to make a copy whenever you want to do something with a container. If it's possible to use a copy like this, then you probably want to use a copy like this. Any questions about this? Yes. So the question is, what happens if we combine these two things together? And the answer is, let's try it like this. These are not going to be easy to combine together on a single line and see what's going on. So I'll combine them together in two separate lines, and we'll see what's going to happen with these two lines right here. Let's visualize the execution, run that. Line 3 is going to create the copy of the list and reverse it. Next, creates the copy of the list that's been reversed. And then we're commanding YS. We're commanding this thing right here, giving it an order to reverse itself again. So it goes from 3, 2, 1, back to 1, 2, 3, undoing the reverse. This one up here, not modified at all because it's pointing to a totally different object. And then everything is in normal order. So reverse something twice and it'll come back to normal. Yeah. In order to, the dot reverse is something that is special to lists, and yes, you can only do this on a list. Another sort of mnemonic for remembering the differences between these two things. So the thing that I remember is always, again, that past tense will give me the copy, and imperative tense, I'm ordering it to change itself. But here, anytime we're using the past tense, at least up to this point in the class, we'll also be combining it with this list command right here to convert it back into a list. And so let's just see like how exactly does this list command work with if we just apply it to lists that haven't even been reversed. So we'll say something like this and then comment out these lines. So this right here, I'm just doing an assignment like that, but also adding the list in front of it. Visualize that execution, walk through, And you'll see that the list function itself actually creates a copy of the list. So there's another one of these implicit copy techniques. There are many ways in Python to make implicit copies. There's another implicit copy. And so I'm bringing this up right now just because you can use the fact that this list by itself makes a copy as sort of a reminder for yourself about that this thing right here must make a copy. The reversed must make a copy because there's a copy operation right here. And this one doesn't have an implicit copy inside of it, so it's not going to make a copy. It's just going to update it in place. The other implicit copy technique that we've seen, again, is something like ys equals xs, like that. This, in practice, in the real world, much more common to do this than it is to do this to make a copy. But I'd say, yeah, like this is used 90% of the time, this is used 9% of the time, and that's used like 1% of the time for lists in particular. For other things that are not lists, this is the thing that's always used. Again, so this is all the material we're going to talk about for this quiz. But this is going to be incredibly important for your homework assignment this week, and basically all homework assignments going forward, getting this memory management stuff right. So I would recommend studying for the quiz before you start the homework assignment for this week. Any questions about? Yes. I'm sorry, that for Wednesday, for next class period, it's only the counting that we're going to do. For a week from Wednesday is the quiz on memory management. Yes. Yeah, so the question is, what exactly is going on in this command right here? So let's visualize this for a second, and actually, let's clean this up a little bit so that we don't have this extra stuff while we're looking at it here. And so the very first line up here, line 1, is creating this list 1, 2, 3. And then when we have xs.reverse right here, this is anytime you have something to the right of a dot, it's going to modify the thing that is to the left of the dot. So this is going to modify this xs. This reverse function is also a function though, so it also returns something. In this case though, the thing that it's going to return is this none value right here. So pretty much every list operation, everyone that I can think of off the top of my head, if it has a dot something on the list operation, like dot append, for example, the return value of dot append is going to be this none value as well. So none is just the return value anytime like it doesn't really make sense to have a return value. So here, this returns none, so ys is none, but it actually reverses the XS list itself. And even if we change this so that like there was a list inside of ys, like that, visualize that execution. So now there are in fact 2 lists down here. Now we run this this command right here, it modifies that. You can see that this list down here, it disappeared because the ys variable is currently pointing to this list, but as soon as nothing points to a list anymore, as soon as nothing points to an object anymore, it'll disappear. And so down here, this is going to make nothing point to this object because the value of this will get substituted for the value of ys, so there'll be no more arrows pointing to this, and that'll go away. Did that answer your question? Okay, we're going to switch over to the notes for today. So again, we're in the topic 3 Q right here. And we're going to talk a little bit in the next 10 minutes about what we call the Q, abstract data type. The queue and the stack are very closely related to each other. And a lot of algorithms will see that their behavior can change considerably whether you substitute or whether you use a queue as the abstract data type or whether you use a stack as the abstract data type that you're working with. Both the queue and the stack are examples of what we call linear data structures. So a linear data structure just means that it's like a list. It's just a collection of things that are possibly ordered. But the difference between a stack and a queue is that the stack, so we saw this picture or a picture like it last week. If we have our contents of the stack, then when we put something in, whatever we get off of the stack, we're always getting it off of the top. So again, you picture it like just a stack of books, and it's really hard to get the book on the bottom out without toppling the stack over. You always just take the book off the top. But a queue is like, this is what British people call lines, that if you're waiting at a queue in the dining hall, it would be very unfair if the very most recent person to arrive was the first person to get their food. So instead, it's the person who has been waiting the longest, or the object that has been in there the longest that's going to come out. It's very common to call stacks FILO, F-I-L-O, first in, last out data structures, and queues, FIFO, first in, first out data structures. In Python, it is possible to use a list to implement a queue. It is possible to use a list to implement a queue, but nobody ever does it. We'll talk about next time why it's super slow to do that. Instead, everybody uses this thing right here called a deque. This word right here, D-E-Q-U-E, is pronounced deque, not DQ or deque. Those are incorrect. It is pronounced deque. And this is what everybody uses for a queue inside of Python. Again, the textbook has a lot of examples of using both the stack and queue. So if you want a more written explanation of these data structures, this is the place to go. In order to, I'm just gonna open up a terminal window here, and we're gonna just see some really short examples of using this deque data type. And here we go. And I'll just run Python 3 like this. And so the line, anytime you want to use this deque, it is something that is built into Python, but if you just type in the word deque like this, you'll get this name error, deque is not defined. So anytime people want to use the deque, it's always from collections, import deque like this. This collections module is built into Python. It has a number of useful data structures inside of it. We'll talk about most of them throughout the remainder of this semester. But this gives us actual access to the deque. And so now if you just type in the word deque like this, then you get this sort of description here. But the important thing is that it's not an error message. If you want to actually create an instance of a deque, so first let's do something like creating an instance of a list like that. In order to create an instance of a deque, it is just DEQUE, and then you pass in, there's a function that you pass in your list to that contains the things that you want in your deque, like that. If I type XS here, that'll visualize the list version. If I type YS, we know it's a deque because it has that word deque, like that. When I do DEQUE.NQ, ENQU, like that, I believe. We just come over here. There we go. Yeah. NQ, DQ. There we go. NQ, and we'll add a new value A like this. Oops. So I'm adding that to my YS right here. YS currently has 1, 2, 3. When I ys.NQ of A, did I have a typo? We use the append. So again, the abstract data type has tells us what the interface is to something, does not talk about runtime implementations. The data structure itself has both an interface and a runtime. In the deque collection over here, we use the append to add something on and pop left method to take something off. So ys dot append a does what you would expect here, puts the a on the right hand side, and then ys dot pop left like this will take the thing on the left over here and remove it off. So ys dot pop left. Look at ys. Now it doesn't have that 1 anymore inside. It just has 2, 3, and a. Anytime you're trying to take something off of the front of a list, then you don't want to do that with a list. You want to use that with a deck. Anytime you're taking something off the front of something, then that's like you're using a queue. Anytime you're taking something off the right-hand side of something, then it's like you're using a stack. In your homework assignment this week, we'll just very briefly take a look at this. There is a pseudocode down here that you'll have to implement. And you can see that it talks about things like queues and stacks. And you will have to interpret, you'll have to say that anytime that it says like create a stack, you know that in Python a stack is a list. And so in order to implement this line of the pseudocode, you'll have to create a list. When it talks about creating a queue, you know that in Python, a queue is implemented using a deck. So you'll have to create a deck for this line right here. The pseudocode down here does not talk about the memory management issues. And so you will have to figure out for yourself what is the right way to make copies of things. And should it be shallow copies or deep copies? And as a hint, you're not going to need to make any deep copies. And you'll have to find out the right way, the right spots to put those in. Yeah, we'll go through a little bit more detail next class period, walking through an example of just what this code is doing and talking about like what is the overall purpose of the assignment here. But I think that'll give you a high level motivation at this point, just that, again, deck, queue, stack, list. And this seems like a good spot for us to stop for today. We have a few minutes left in class. Happy to answer questions that people have. Yes, question. Yeah, so the question is, are we using the deck instead of a list just because it's faster? And the answer is yes. We'll see that it's a lot faster, that there are some situations where using the deck will make code run in milliseconds, whereas using a list could make the code run in years. And we'll formalize all of that starting next class period. Yep, good question. Again, if anybody else has more questions, happy to stick around and chat about them, but that's the end for today.